Hi, I'm Scott Campbell with Solve 3D, and today I'm here with David Jaron and Kevin Miller. Kevin and David did a very well-received talk at GeoWeek 2023 in Denver on the topic of applying deep learning to geospatial data. We've had many requests for a recording of that, but unfortunately, it wasn't recorded. So we're going to do an off time slot recording of it for you here now. And with that, I'll turn it over to Kevin and David.
Yeah, thanks, Scott. So yeah, welcome to our overview on how deep learning can be applied to geospatial data. And just to reiterate here, I'm Kevin Miller, the CTO here at Sol3D, and I have with us David Jaron, one of our AI geomatics developers. So we have a lot to talk about, so let's just get started. So these days, every time you turn around, you see or hear something about artificial intelligence in the news, from identifying giant pandas to trying to figure out the stock market. Chat GPT is huge these days. So, it's everywhere in all areas of our life. So, and as you can imagine, there's lots of money being invested into this AI technology. So let's take a quick step backwards and define some terminology first. So when you look at artificial intelligence or AI, it's essentially a broad concept of having computers behave like people. So this doesn't necessarily mean that it's some magical black box program that classifies a point cloud. No, it could just be, a simple program that adds a series of numbers together. It's basically a general term of how computers behave. So kind of moving into machine learning, it's a little bit more specific. It's all about taking historical data and trying to predict the future. So, getting a computer to learn that data and calculate some outcomes or some predictions. And in the realm of AI, machine learning is a subset of AI. And where it gets really interesting is when you start thinking about deep learning or talking about deep learning. Deep learning is yet another subset of machine learning. And like machine learning, it uses historical data to predict the future. But the way it does this, though, is it tries to mimic the human brain using neural networks and essentially forming the pathways from node to node of complex formulas of how to interpret that data. And then finally, you may have heard of a field of study called data science. It's a field where analysts, engineers, and scientists comb through tons of data trying to find answers. And not surprisingly, this field overlaps in they use technology like AI, ML, deep learning to help get their answers that they need. So let's just take a quick look at an example of deep learning, say privacy blurring. So in this clip here, we're located in London, England at the Tower Bridge, and you can see quite a few vehicles and people here. In Europe, and more so over here as well, privacy laws are being enforced. And for people that collect the data, it's it's something that we should be concerned about. So what we're doing here is we're running these photos through a blurring algorithm, which is using deep learning to find those vehicles and people, and then apply a Gaussian blur on the object of interest here. So very practical use case in our industry. If you took a look at this problem like this in your data, say with privacy blurring, and you're trying to solve, maybe you're trying to write a program that will do something like this, you really need to think and do some research on this topic. So the first thing is obvious. You try to find an established method for doing something like this. And in this case, you'd have to write a program that would analyze each pixel one by one in the image and look at the color patterns and shapes and identify things. It'd be virtually impossible. It would never be reliable. So in this case, the data is highly complex. There's lots of variety from image to image. And essentially the only way to solve this problem right now manually is to get a human to study each image manually and find the objects that they're looking for. So in this case, it's usually that means that it's a good candidate for something like deep learning. So why deep learning? Well, If it isn't obvious by now, it can produce results faster than we can. It's more flexible and adaptable to traditional algorithms. And I mean, you may have written some awesome program that can identify trees in a point cloud, but if you need to adapt it to differentiate different species of trees or different shapes of trees, this might be super difficult and time consuming. So to update your program. So deep learning can start to learn this more quickly, and most importantly, it can identify those complex patterns that we as humans may not be able to see or understand. When looking specifically at geospatial data, deep learning is a great candidate for doing things like classifying point cloud data. It might examine many characteristics of the point cloud, like intensity, reflectance, normals, different RGB colors, etc. In imagery, it's really good at identifying those and finding those objects. And once you find those objects, you can start to use other techniques to extract the position and measure the size or quality or conditional information on those objects. So this video shows some clips of some of the deep learning things we've worked through in the last couple of years on geospatial data. So classifying point cloud data automatically, maybe examining orthomosaic or satellite imagery and finding all their, say, vehicles or paint markings, or even using some mobile mapping data to find traffic lights, signs, etc., and extracting their positional information. So as you can imagine, there's so many use cases in using technology like this, and there's so many ways that researchers and different companies are tackling these processes. So I'll pass it over to David now to get into some of those details.
Yeah, thanks, Kevin. So Kevin sort of broke down the difference between AI, machine learning, and deep learning. So to get into the weeds even more, deep learning software, the current offerings on the market can be broadly categorized into three distinct types, which we refer to as ready-made, do it all yourself, and do the training yourself. So the ready-made solution is essentially everything's ready-made for you. You don't really need to do any work or any spend too much time figuring this out. They typically are cloud-based, which means you don't need any of your own hardware. You just need an internet connection, pay per use, which means that you only pay when you need to use it, and the models are pre-trained, so you don't need to do any of your own training. Those are all sound like really good upsides, and they are in some cases, but cloud-based has the downside of you must upload data, which can be very time-consuming and also costly because it tends to cost a lot of money to host things on the cloud. Pay per use is great if you're only doing it a couple times, but that cost continues to grow the more often that you're using this deep learning solution. And the models are pre-trained, which does mean that you can't change the model yourself if you're looking to find something, a different type of object, or classify different types of point clouds or different type of data, which takes away one of the main advantages that deep learning solutions have over other more traditional algorithms. The second method is the sort of the opposite, which is a do-it-all-yourself solution. Obviously, this offers excellent flexibility because you're custom programming it to do whatever you want it to do. Your data stays secure because you're accessing it yourself, you're using it yourself, and you're hosting it yourself. The models can be strategic if you have some means by which you can you maybe have special training data, or you have better developers than anybody else. Your models that you have might be the best, and it might be better than your competition. And you can also control how accurate this model is, the one that you're developing. And unfortunately, the somewhat fairly obvious downsides of the do it all yourself is that you have to do it all yourself. It's right in the name. So you need to have your own training data, you need your own hardware, you need time, and probably the most annoyingly for a lot of companies who are looking at this is you need the expertise. You need to have developers and machine learning experts to develop these methods for yourself, which obviously takes time and money. What we've found is sort of a Goldilocks middle ground for some of our clients is a train it yourself model, which is sort of a combination of the two, where you take the benefits of both, and you get rid of some of the negatives. So training it yourself means that you have excellent flexibility, your data stays secure, and your models can be strategic. You control the accuracy of the model, as well as the model can be tailor fit to exactly the type of object or use case that you're looking for. And as I was saying before, it kind of reduces the downside. So you only need you need your own training data, and you need your own hardware. Excuse me. So I mentioned before that you can have a tailor-made model with the previous type, the train it yourself model. So I want to just quickly take a look at a use case. In this case, we're going to look at an infrastructure asset survey of light poles. So if I ask you the question, what does a light pole look like? I mean, it sounds sort of like a stupid question. And if I was asking you guys that question, it is a dumb question. But when you're asking that question to a machine, a computer, it doesn't know that until you tell it what it looks like. So all of these are pole-like objects. They're all in the same data set. They're all within maybe 100, 200 meters of each other within the same building complex and parking lot. So depending on your use case, what you're looking to do with this, some of these might be objects you're looking for, and then some of them might not be. For example, the far left image is certainly a light pole, but it is not the sort of standard light pole you'd see along a street. So if you're looking to do an infrastructure asset survey, you might not be looking at these more pedestrian walkway light poles, or maybe you're looking to do something more comprehensive and you want both. In either case, though, you might not be looking to get the flagpole, which is the rightmost image, but it is very similar looking objects. So you both need to train the model to find what you want and to not find what you don't want, which is why the training data is really important. It's probably the most important part of the whole process, is having good training data. So the training data being good means that it's representative. It shows all varieties and angles of the desired object that you're looking to find. Complete, which means all within your training data, all examples of those desired objects need to be identified in the training data. And you want to minimize any errors in that as much as possible, which isn't surprising. Obviously, you want it to be as high accuracy as possible. So I said just before that the training data is really important, and maybe even the most important. And the reason for this is because if you do it right, you only have to train the model once, essentially. So you take your data, you prepare your training data, you make sure that it has all those key factors, you train it, and then you can use that model that you develop to classify many data sets, and then you essentially do all of the hard work at the beginning, and then after that you get to just continue to use that model over and over again. So the first step in getting your training data into a good state is to label it. We're going to go through this sort of example with imagery. So you need to label the image with examples of the object you're looking for. In this case, just a quick sort of sped up example of classifying traffic lights along this streetway. As you can see, there's quite a few objects, and in this example, I think we only grab 20 to 30 actual lights, and then so we only classify a few objects and then move on to the next step, which is,
There we go.
Oh, I'm definitely clicked back to clicked forward to me. So the second step is doing the actual training, which is sending those labels that you create in the labeling step into the actual algorithm. And as you do this, you choose a few parameters for the model. And as it runs through, if your training data was good and all of the parameters that are set up in your model are good, you should see over time the accuracy of your model increase and the false negatives decrease, which essentially, without getting too much into the weeds, means that it's finding what you want it to find, and it's not finding any incorrect examples of that. I don't know why this keeps playing twice. There we go. And then the third step is once you have that model generated, you can use it to classify other data. So it might be that you had a training data was a small subset of the total data that you're looking at, or it might be a previous example in a similar instance and you're looking for the same type of object, but in which case you can apply the training model to this new data. And it should be able to find a bunch of examples of the similar types of objects all around in the point cloud, further down in other places that you weren't looking at initially. So especially in the case of a 2D image, labels aren't usually sufficient in for geospatial applications because you know where it is in an image, but not in 3D space. So usually you would need to utilize other assets such as LiDAR or some other kind of depth or point cloud processing, or you can also do matching and projecting labels into the 3D space to find or estimate the 3D position of these objects, which is what we have here. Essentially what this does is just projecting the label information out and trying to find other areas where that same object has been found to triangulate the 3D position of this. Yeah, so deep learning models can also provide a means to augment other data, even without training on that data type. For example, in this example, we use training and a machine learning model that we developed to find information from aerial imagery, and we project that classification down onto the point cloud. Oh, didn't actually. So you can see here that we have this orthomosaic with a series of classifications and areas that we found of vegetation, buildings, water, etc. And then you can project these down onto the point cloud and have a classified point cloud, even though maybe you didn't have sufficient information to create a model, or in some cases that type of information isn't easy to discern from that data type. I'd just like to quickly at the very end just talk about, we have a deep learning workshop that we run every so often, which basically just goes over sort of more in depth what we talked about here, fundamentals of deep learning, how it can be applied to geospatial data, as well as some useful tips. And it's a hands-on workshop, so you can really get a feel for what's actually happening and how to use all this stuff in a productive productive way. Thanks for coming to hear this talk online.
Yeah, thanks for that, Kevin and David. Some of the questions, maybe you can answer some of the questions that I typically get when people are talking to me about, applying deep learning to geospatial data. So the first one I get is like, do you have any pre-trained models that I can get started with?
Yeah, we do have some pre-trained models on our support portal. They're kind of more examples though. So we do have some we have one that does an 8 classification model, or 8 different classifications on aerial data, and another one, I think it's 6 classes on a mobile mapping data set, specifically with point clouds. We also some imagery examples. However, I'd like to warn you that they are just examples. They're trained on that specific type of sensor and that density of data. So, if you're running those models on maybe some data that you've collected that's an entirely different density of point cloud or something like that, you're going to get, you may get good results or you may get different results. So they're meant to be used as a starting point or an example of what the technology is capable of.
Another question I get is, can I use deep learning to classify ground in my point cloud data sets?
You could. However, we found that in most cases that, as I was pointing out in one of those slides, ground is a a method. There's already a kind of proven statistical analytical method, programmatic method, we'll call it, on the data. And those, from what I've seen at least so far, unless you do a lot of training, those programmatic methods are still quite a bit further along there. They work very well, and you get way better results in terms of accuracy. So that's where I'd start with if you're just looking at ground. Obviously, if you're looking at some more classes besides ground, yeah, then there might be a good candidate for deep learning.
David, image-based models seem to perform better and seem to be more accurate than point cloud-based models. Why is that?
Yeah, that one's that's a good point. They're also quite a bit quicker typically, and the reality of it is just that images are easier to deal with because they are 2D versus point clouds being 3D. The fact that there's simply less information means you can use more examples, which provides a better context for the machine learning model. You can typically iterate those models further because they don't take up as much memory, and because they were easier to work with, especially initially, there's just been more research done on those topics, and they tend to have a broader scope of application where there's a lot of different fields, not just geospatial, that are interested in image processing and identifying objects in imagery. So it's that is a fairly advanced field, whereas point net classification using deep learning and neural networks is still, I would say, maybe not quite in its infancy, but it's like it's like a toddler level. It's still a work in progress for the most part.
Yeah, right on. Now, ChatGPT has been in the news a lot lately. Are we going to be seeing ChatGPT applications in geospatial data anytime soon?
I doubt it. They like ChatGPT. Yeah, it's a great technology. The one thing about it is it's a completely different neural network. It's built differently. It's built for studying languages and figuring out how sentences and words fit together, and that's typically what it excels in. How that can be applied to geospatial data is still, back to David's point, it's still pretty new in the world of this technology. So I don't think we'll see anything soon, but you never know, I guess.
I might be able to write this presentation for us in the future, though.
Yeah,
yeah, totally.
It's true.
Yeah.
David, one application that we get a lot of requests for is to identify and locate transformers on power poles. What tips would you have for people who want to use deep learning to go do that?
Sure thing. Well, the first thing I would say is make sure that you have data where those objects are identifiable and unique looking in some way. So if that's point cloud, it means you need high enough resolution that those objects can actually be identified. A lot of times people want to be able to find everything, but their point cloud density is just simply too small. If you can't figure out where it is in the point cloud, the machine learning is not going to be able to either. The same thing goes for imagery. That's sort of like a golden rule. Like if you can find it, the machine learning can find it. But if you can't, it has no hope because your training data is not going to be good enough. As well as that, I would say there's some sort of advanced tips that you can do, such as in a lot of, especially on the point cloud side, if you are looking for really small objects that don't make up a large portion of the point cloud. Typically, point clouds will be, say, if you're in an urban setting, it's probably like 80% ground, 5% buildings, another 10% vegetation and other random objects, noise, and then the 5% remaining is other random objects like power poles, power lines, etc. And they make up such a small portion of the actual total point cloud that when you're training, as it iterates upon the model, it's looking to improve those accuracy numbers. But when you have those objects make up such a small amount of the point cloud that a lot of times they won't matter to the machine learning. It just says, well, these make up such a small amount, and it essentially becomes like a random error, and it's probably not going to do a good job finding those. So one thing we found helps in cases like that is removing ground, because ground tends to be one, you can find it using analytical methods pretty easily. So a lot of times what we recommend is removing the ground first. and then training just on the remaining point cloud, because it'll mean the objects that you actually really are interested in finding make up a greater percentage of the point cloud, so it'll be easier to train on that. And another thing that I would say is really important or really helpful in this case is looking at what type of data works best for the thing that you're looking for. And I would say in a lot of cases, it might be easier to identify those types of, especially like transformers and things that are on or attached to other objects. A lot of times it's easier to find those kind of objects in imagery. And then once you find them in the imagery and you get their 3D location that way, you can find, you'll be able to find those in the point cloud as well. Or it's all about utilizing all the data you have and using the data that best fits the application or the use case that you're actually trying to execute.
Right on. Thanks, guys. Really appreciate that. I can see why this talk was so popular and well received at GeoWeek. I'm going to put up the QR code there for people who would like to take our hands-on workshop. And yeah, just if you're interested in that hands-on workshop, just go ahead, hit the link and register for the course. Once again, thanks very much, guys.
Yeah, thank you.
No problem.